stars being tiny, the sun and the moon being tiny, and everything close to us.
So there's a rumour going around that the Earth spins on its axis, roughly 360 degrees in 24 hours. There are a number of experiments and demonstrations that can prove this. One such proof is the ability of a spinning gyroscope to remain rigid in space whilst the Earth spins below. The US Navy put out a training video in 1960 explaining this using diagrams, as shown here. The link to the entire video is in the description. Not only is it alleged to remain rigid in space, the angle that the gyroscope, quote-unquote, appears to rotate is said to be measurable using a very simple equation which is wholly dependent on your latitude on Earth and the axial orientation of the gyro. So, through maths, and based on an assumption that a spherical Earth is rotating about its axis, we should be able to predict the angle that the gyroscope will rotate over a given time at a given latitude. This notion has been accepted as fact by modern-day science without a shred of evidence to support it. Nowhere can I find any video that demonstrates this apparent proof. I found the same assertion made about apparent drift all over the internet, including on aviation websites like this one, which gives more illustrations and the same equations for calculating the drift. My experiment/demonstration, which is coming up next, will be done using the Super Precision Gyroscope. These are manufactured here in England, and if you haven't guessed by the name, they're works of precision engineering to exacting standards. Here's a video by the manufacturer.
At last, a gyroscope that just works properly, just like you've always wanted. Novel, innovative, and precise. The fascinating properties of gyroscopes, with their ability to maintain position and seemingly gravity-defying properties, will mesmerize both young and old alike. The Super Precision Gyroscope is beautifully designed and manufactured to the highest precision. The gyroscope comes complete with its own electric starter motor. There's no need for string to start it. It's less fiddly, spins the gyro much faster, and doesn't put load to the delicate bearings. Even when spinning at 12,000 revolutions per minute, there is hardly any noise or vibration. And when it's up to full speed, it spins for a very long time. The gimbals are modular, allowing you to construct numerous configurations. You can build the standard setups to demonstrate nutation and precession, plus you can make your own setups to perform your experiments. The parts screw together, as well as 7 places around the gyroscope frame. It will provide hours of amusement and learning by showing just how gyroscopic forces affect our daily lives. Today, they can be found in aircraft, satellites, and many other guidance systems. Made from solid brass, aircraft-grade aluminium, and stainless steel. All of the components are precisely manufactured with state-of-the-art machines. We use some of the most accurate equipment available to detect the slightest imbalance. The brass rotor is dynamically balanced to within a few thousandths of a gram and assembled with ultra-low noise bearings. This meticulous attention to detail produces a true precision instrument that will last for years. The set includes the Super Precision Gyroscope with electric starter motor and gimbals kit, complete with manuals and storage case. Our gyroscope is ideal for schools, universities, or anyone who just enjoys using well-engineered kit. It also makes a great gift for those with inquisitive minds.
Okay, so this is the setup I'm going to be using. You'll notice this side, there's like a blanking insert that goes into the bearing housing on this side. And on this side you attach the motor, so the hole is empty, just with the spindle sticking through. So I quickly realised that when I spun this thing up, due to the presence of material here and the absence of material here, there was a weight imbalance. So I contacted the manufacturer and asked them if this is expected, and they confirmed it was, and offered to make me a one-off insert to go in here for free. But they also suggested that what I could do is use some Play-Doh, some kids' plasticine. So I did that. I got some of my daughter's Play-Doh, just spun it up to speed with the motor, and then inserted this into the hole. That seemed to do the trick. I was able to balance it perfectly. Before I put this in, the extra weight caused this side to drop every time, and if it was over here, it would drop this way. So that's how I overcame that. I've attached the whole setup to a protractor, which I've blue tacked to the table, and I've blue tacked the actual the frame to the table as well. So this here is the angle that we're looking for. So what we're looking for is this effect. See how the gyro wants to rotate and stay in the original orientation? Well, that angle that it's rotating, that this bar appears to be rotating over the vise, that is the angle that we're looking for. That is the angle that we should be able to calculate this gyroscope moving due to the rotation of the earth underneath us. So without further ado, let's get on to the test. So I've just attached the motor there. It actually takes 4 AA batteries to power it, and I've run this test quite a number of times now and put quite a few batteries through it, so I kind of know how long they're going to last and what sort of sound comes from the motor, depending on how much power is left in the batteries. And I'd say there's about probably 75% power left in them at the minute, and that's based on 12,000 RPM maximum. That's probably about 8 or 9,000 RPM for this particular test. So it's getting up to speed now. I'm going to remove the motor and replace it with the piece of Play-Doh to get it perfectly balanced. And now I'm going to demonstrate some precession by gently pressing on the horizontal bar there. And now I'm going to line it up as best I can, so that you cannot see the brass flywheel from above, and it's as sort of straight up and down as possible. So if we just take note of where we are now, at you can see a 0 on the top right, just to the right of the bar. You can see a 0 just there, and you'll note that you cannot see the brass flywheel from above now. So we are sort of dead centre above it. So now it's just a waiting game. So while we wait, let's just have a look at a brief history of the gyroscope, up to the point where it was first proposed that it could record the spin of the Earth. So this is just sort of one example that I found on the internet. There are lots and lots of different accounts, and they all differ slightly, but this one seemed like a sort of all-round recount of history. So in early times, people discovered the spinning top, a toy with a unique ability to balance upright while rotating rapidly. Ancient Greek, Chinese and Roman societies built tops for games and entertainment. The Maori in New Zealand have used humming tops with specially crafted holes in mourning ceremonies. In 14th century England, some villages had a large top constructed for a warming up exercise in cold weather. Tops were even used in place of dice. It was not until the late 18th and 19th centuries that scientists and sailors began attempting to use spinning tops as a scientific tool. At the time, sailors relied on sextants for navigation, measuring the angle between specific stars and the horizon. This method was limited, however, if choppy seas or fog obscured the true horizon, or clouds obscured the stars. Serson, an English scientist, noted in the 1740s that the spinning top had a tendency to remain level, even when the surface on which it rested was tilting. He suggested that sailors could use it as an artificial horizon on ships. Unfortunately, when Serson went to sea to test the idea, the ship sank and everyone was lost. A French scientist in the 19th century, Fleury, created a top that was continuously powered by air jets, blowing into mini buckets on the rim of the wheel, a process that had been used for thousands of gyros since. The first modern gyroscope was designed in the early 1800s by Johann Gottlieb Friedrich von Bernberger, a professor at the University of Tübingen in Germany. It was made with a heavy ball instead of a wheel, but since it had no scientific application, it faded into history. In the mid-19th century, the spinning top acquired the name gyroscope, though not through its use as a navigational tool. French scientist Léon Foucault had experimented with a long, heavy pendulum in an attempt to observe the rotation of the Earth. The pendulum was set swinging back and forth along the north-south plane, while the Earth turned beneath it. Foucault corroborated the observation by using a spinning top in a similar manner. He placed a wheel, rotating at high speed, in a supporting ring in such a way that the axis of the spinning wheel could move independently of the ring. In fact, the supporting ring moved over the course of a day, as it was connected to the surface of the rotating Earth. The axis of the wheel remained pointed in its original direction, confirming that the Earth was rotating in a 24-hour period. Foucault named his spinning wheel a gyroscope, from the Greek words gyros, which is revolution, and skopin, which is to see. He had seen the revolution of the Earth with his gyroscope. So, from Wikipedia, Jean-Bernard Léon Foucault, born 18th of September 1819, was a French physicist best known for his demonstration of the Foucault pendulum, a device demonstrating the effect of the Earth's rotation. He also made an early measurement of the speed of light, discovered eddy currents, and is credited with naming the gyroscope, although he did not invent it. Foucault was the son of a publisher in Paris, where he was born. After an education received chiefly at home, he studied medicine, which he had abandoned in favour of physics due to a blood phobia. He first directed his attention to the improvement of Louis Daguerre's photographic processes. For 3 years he was experimental assistant to Alfred Donné in his course of lectures on microscopic anatomy. In 1851 he provided an experimental demonstration of the rotation of Earth on its axis and became well known to the public by Foucault's work. Foucault achieved the demonstration by showing the rotation of the plane of oscillation of a long and heavy pendulum suspended from the roof of the Pantheon in Paris. The experiment caused a sensation in both the learned and popular worlds, and Foucault pendulums were suspended in major cities across Europe and America, attracting large crowds. In the following year, he used and named the gyroscope as conceptually simpler experimental proof. In 1855 he received the Copley Medal of the Royal Society for his very remarkable experimental researches. In 1862 Foucault was made a member of the Bureau de Longitudes and an officer at the Legion of Honour. He became a member of the Royal Society of London in 1864 and a member of the mechanical section of the Institute a year later. He is also credited with determining the speed of light to be 298,000 km per second, which is only 0.6% in error of the currently accepted value, and devising a method of testing the mirror of a reflecting telescope to determine its shape. So, reading between the lines, he was a man of significant academic accomplishment and recognition at the time. One has to wonder then why, when you read the Wikipedia article about Léon Foucault, does it have this one line at the end? Near his death, he returned to Roman Catholicism that he had previously abandoned. Draw your own conclusions. So going back to the test, we've exceeded 6 minutes now and there's no observable movement. You can still see the zero to the right of the bar in its entirety, and you still cannot see the brass flywheel from above. So how much should the gyro have precessed? What angle should the gyro's axis have moved? The calculation is the sine of the latitude times 15 degrees per hour. My current latitude is exactly 53.06 degrees north. So the angle in which the gyro should have moved in 6 minutes is 1.2 degrees. Now this doesn't sound a lot, but let's assume that Léon Foucault's experiments were performed in Paris. He should have seen even less based on his latitude. And let's not forget that he didn't have an electric motor spinning his gyro up to 9,000 RPM. So I'm just going to stop it now. You saw then that there was still plenty of energy left in that flywheel, and it was able to precess when I moved it. So out of sheer curiosity, I decided to fix the motor to the gyro and put a counterweight on the other side, which is slightly heavier than the motor, so I counterweighted the counterweight with more Play-Doh until I got it perfectly balanced, and ran the motor for, I think it was 10 minutes on this one. I'll show you a few minutes of it, but I'm not going to show the whole lot. If anybody wants me to, I can upload the whole video. It's pretty boring, it just does nothing. But this is now the equivalent of, I guess, modern navigational aviation instruments, you know, with sustained rotation. In Foucault's tests, the rotational velocity would have been continually decreasing. If the batteries are fully charged, I can actually get about 19 minutes of sustained rotation once I've taken the motor off, which is a hell of a lot on this gyroscope. I did actually try putting the motor on and keeping it on and just running it, I think it was for about an hour with a full set of batteries, and still I observed absolutely no movement whatsoever. So it appears that whether you've got the motor on or you've got it up to speed and then taken it off, it doesn't matter, it still doesn't move. So I just cut to 10 minutes. Like I say, if anybody wants me to upload the whole 10 minutes, I will. Or if anybody wants to see me put it through for an hour with the motor on, I'll video that and show you no movement as well. Bearing in mind that after an hour, it should have rotated about 12 degrees. These are some of the gyros that Leon Foucault used in his experiments. The large one at the back on sort of the wooden tower was a later edition. That one wasn't manufactured until 1867. But the ones at the front were all part of the same setup, and they were demonstrated in 1852, so 15 years earlier. And what you do is you take the flywheel out of the gimbal, the brass gimbal stand on the right, and you place it in this wooden sort of housing and spin it up. Quite how it was spun up isn't clear, I couldn't really find that out, but once it's up to speed, they then take it out of this wooden frame and transport it back into the brass gimbal set. Then you see the long pointing arm, the white pointing arm, coming from the sort of axis, the rotational axis there, onto the little measuring stand, which would have had graduations marked on it. And then with the eyeglass, he would look through it and see what the sort of rotation is. So you can see what we're looking at is a very, very tiny amount, and that's due to the fact that he couldn't spin his gyro up for very long back then. Some of the sources I found said it was only between 150 and 200 RPM, which I'm sure doesn't sound right, because I think I could spin that up quicker with a piece of string wrapped around the spindle. But that's what it says. So he wouldn't have had long to actually get this reading before the gyro slowed down to a stop. What, maybe 3-4 minutes? Let's give him the benefit of the doubt and say 5 minutes. So based on a latitude in Paris, that's less than 1 degree's movement in 5 minutes. So you can start to see why he needs the extended arm to sort of exaggerate the angle, and the sort of magnifying telescope looking device, because the movement is extremely small. Now this movement could purely be down to a weight imbalance like I had, or it could be the friction in the bearings. Remember, this was 1852. Technology wasn't as it is today. If you remember on the manufacturer's video, they said that there's absolutely no load on these bearings. So whether he was lying about seeing any movement, or whether he did see some movement, but it was just due to the inferior setup he had, I guess we'll never know. Now some of you might be thinking, aircraft directional gyros do actually drift, and this is true. The pilot has to realign the gyro compass with the magnetic compass every 15 minutes. That's good practice, I know that from personal experience. And this is said to happen because of apparent drift. They say it quite clearly in the 1960s US Navy video that I've linked to. They blame this completely on apparent drift. I'm going to try and simulate what I think is happening, and why pilots have to realign the compass every 15 minutes. So what I've done is I've aligned the vertical peg here with the vertical casing of the gyro there, and I've aligned it, this bar, the bottom bar there, with this foot here, with this third foot. So I'm going to simulate turbulence, vibration from the aircraft, track changes, by just wiggling this bar. So this is only a gradual thing. Every 15 minutes it drifts out slightly, and it varies as well. Sometimes it drifts quicker than other times, and as pilots will be aware, after any sudden or hard banks, or sort of large turns, the compass seems to drift even further and quicker. So let's realign the. It's not been doing it for long enough yet. Let's give it a few more. There you can see it's already drifting that way, and it doesn't matter which way. It just depends on the bias of the turn, or the bias of the number of turns in any particular direction. It will tend to drift that way. Now you can see, look, it's gone quite a long way out now. So that's what I think accounts for the corrections that the pilot must make every 15 minutes to realign the gyro compass with the magnetic compass. And what of the artificial horizon? That's a gyro as well. Why doesn't that need resetting every 15 minutes? Surely that would be subject to the exact same drift as the directional gyro. But it's actually considered bad practice to realign your artificial horizon during flight, because you don't know whether you're aligning it to a straight and level orientation. So why does the directional gyro drift, but the artificial horizon gyro doesn't? Well, I believe it's because the directional gyro is 2-axis. So it's allowed to move this way, and it's allowed to move this way, but if it moves this way, the actual flywheel moves with it. In a 3-axis gyro, it can actually move this, the axis can move this way, but the gyro flywheel stays aligned like this. But logically, if the directional gyro precesses due to wanting to remain rigid in space, the artificial horizon gyro would necessarily have to do the same, but it doesn't. So for all the naysayers out there who think I might be somehow deceiving or I'm doing something wrong, be my guest. Get yourself a gyro and demonstrate it rotating or appearing to rotate and to the exact angle, because it should work like clockwork. If you're not willing to do that, then you are just accepting the word of some dude that performed an experiment 164 years ago that you've never witnessed yourself and nobody else alive today has ever witnessed. After all, it's a really easy experiment. All you need to do is get a perfectly balanced gyroscope, set it running and wait. You can't really do much wrong. Thanks for watching.
The complete universe, housed within the Earth. Does it seem possible? Does it seem strange?